Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to continue our discussion about how to find the area between functions and the x-axis. In our previous lesson, we just got a little taste of that when we talked about what the area under velocity functions can represent in terms of total distance, net distance, or displacement. And now we're going to move more generally into any types of functions. We're not necessarily going to focus on units today or word problems. We're just going to be talking about how there are different ways to figure out or estimate area underneath functions or between functions in the x-axis. Keyword for today keywords for today are Riemann sums. And essentially these are ways to estimate the area under functions that are made up of curves. So again, at the end of last lesson, we talked about, it may be fairly easy when our function is made up of segments to find the area underneath them. But if it's made up of a curve, well, we don't really have area formulas for, curve shapes that are, partially straight segments, partially curves, etc. So the best we're going to be able to do is estimate. We're not going to be able to find the exact area today. That's going to be left for a later lesson, again, when we talk about how to evaluate integrals. So the first type of Riemann sum we're going to talk about is a rectangular Riemann sum. So our goal is to estimate the area between this blue curve and the x-axis. So we're trying to figure out the best approximation for this area right here. Well, what we can do is we can sketch some rectangles. So let me actually get rid of this. We could break this up into some rectangular shapes and just add those areas together. So, and again, there's many different ways we can draw these rectangles. So I'm just going to do rectangles that have a, width of 2. Okay. So if I could find the area of all of those rectangles, then it would be an estimate of the area underneath the blue curve. So let's go ahead and do that. Call this rectangle, Let's call this rectangle 1, 2, 3, 4, 5. One day there'll be a video where that doesn't happen throughout the entire video. Area of rectangle 1, well, that's going to be 2 times 7, so that's going to be 14. Area of rectangle 2, that's going to be 2 times 4, which is 8. Area of rectangle 3, also 2 times 4, which is 8. Area of rectangle 4, that's going to be 2 times 11, so 22. Same thing for rectangle 5. And for rectangle 6, we have 2 times 6, which is 12. So if I add those all together, my area estimate is 86. Just had to make sure I was doing my math correctly there. So this would be one estimate of the area. The problem is, right, I didn't really give you that much direction here with what types of rectangles I should have drawn, right? There was nothing that said I had to use exactly 6 rectangles. I could have also drawn my rectangles differently, right? Maybe you're thinking, this first rectangle that you drew, we could have estimated it a little bit better if I had drawn this one, right? And that's true, right? This was just kind of my interpretation of the rectangles that would give us a good estimate. When we talk about Riemann sums, they give you more constraints. So they have several different ways of drawing rectangles that provide us with different estimates. And that's what we're going to look into today. So it's going to be a little more structured, and they're not just going to say, draw whatever rectangles you want in here to give an estimate. They're going to say, no, you need to draw your rectangles according to this method. So we're going to look at, there's 3 methods for rectangles that we're going to use, and then there's actually a trapezoidal method that we'll use at the end. I'm just going to go through an example of each one to show you these different types of estimates, some being better than others, depending on what your function looks like. So let's get started. We are going to be using the same function. Let me just make this a little smaller. We're going to be using the same function for all of these estimates, and that function is right here. So you may just want to write that down off to the side, because you are going to need to be substituting into that function quite a bit as we try to figure out different y values. So the first one we're going to do is a left Riemann sum with intervals of length 2 units. So this means we're going to be drawing rectangles that each have a length of 2 units, or sorry, an interval of length 2 units, which means 2 units on the x-axis. Now, we are starting with the interval 1 to 7. So I'm going to draw my first rectangle. It's going to go from 1 to 3, right? 2 units on the x-axis. Now, because this is a left Riemann sum, we are only going to go as high as the function does for my left endpoint. In this case, that's at x equals 1. And that's going to tell me what the height of my rectangle should be. Okay. For my next rectangle, see that one in blue, I'm going from 3 to, I'm going from 3 to 5. And because this is a left Riemann sum, I'm going to be looking at the y value of the left endpoint on 3 to 5. So at 3. So this rectangle is going to go all the way up there. My final rectangle from 5 to 7, the left endpoint goes up here. So my third rectangle looks like this. And you may say, well, that's not the best, those aren't the best 3 rectangles you could draw. Well, maybe, maybe not. However, that's just what a left Riemann sum is. And that means that everybody who does a left Riemann sum is going to come up with the same answer here. Their rectangles should all look the same. Now, here, some of these y values, you can't tell what they are, right? There's one like for the blue. If I look up at this y value, I know that that's at 8. But for the pink and the red, you're actually going to have to use the function to figure out the height of these rectangles. So that's why I said we need to pay attention to that function that I circled in green. So the area of the red, I was going to say I was going to color coordinate these, but then I drew pink. So the area of the red rectangle, not what I wanted. So area of the red, base of the red rectangle is 2. Height of the red rectangle is this y value right here, which is f of 1. So 2 times f of 1. And I'm not going to write out all these in-between steps because we can just substitute this right into our calculator. This function right here, the easy way to do these problems, because you're going to be using this function a lot, is to put that function into y1. Then go to your home screen, and to evaluate this right here, well, you're going to do 2 times, click on alpha trace. So if you're on a TI-84, alpha trace, it gives you a list of y1 through y0. Click on y1, so it brings up this on your home screen, and then in parentheses, put 1. That will end up giving you what that value is. So 2 times y1, or 2 times f of 1, is approximately 13.333 And because I'm in the middle of a problem, I'm going to go to 4 decimal places. For my next one, that's a little easier. Area of the blue, I'm doing it in light blue so we can see it a bit easier. It's just 2 times 2 times 8, so 16. That point just falls right on the edge of a box, so we know that that y value is 8. If you want to check, you could punch it into the function, but f of 3 does give you 8. My last rectangle, this actually ends up being the same area of the red. I get 2, in this case, times f of 5, which does give me 13.3333. So I've got these 3 areas. I need to add all 3 of those together, and I'm going to get area of the whole is approximately 42.667 or 42.666, depending on whether you rounded or truncated. Now, this is an estimate, right? It's not the exact area. But let me show you again just that integral notation. So you have an idea and you're used to it by the time we actually get there a couple lessons down the road. So what I am estimating here is this. I am estimating the integral from 1 to 7 of f of x dx. And we'll talk about, what that f of x dx, why we have those there. But again, this right here represents the area under the curve. From, or we can say on 1 to 7. So this estimate right here represents that, 42.667. That is what we have estimated. Okay, so that was a left Riemann sum. We're now going to move on to a right Riemann sum. I'm going to have to rotate here. There we go. Here's just more left Riemann sum practice. We're not going to go through these. You can do these on your own. All they've done is change the base of the triangle. So if you look at the approximation number 2, they're making the base of the triangle 1 unit. So you're going to have more rectangles. And for approximation number 3, you're going to have a base length of half a unit. So you're going to have even more rectangles. So it does get a little tedious, but it's not difficult math. It's just tedious because you have more rectangles to add their area, more rectangles areas to add together. Let's talk about right Riemann sums though. And we will do the one on the left again. So length of 2 units. Make this a little bigger. Okay, again, same function, same graph, etc. Now for a right Riemann sum, and we're starting at, we're doing the interval 1 to 7 again. So intervals are 2 units. So I'm going from 1 to 3, but this rectangle now, it's the right side of that interval that determines the height of the rectangle. So my second interval will be 3 to 5, but it will be 5 that determines the height of that rectangle. And then finally, let's do orange. Going from 5 to 7, it will be 7 that determines the height of that rectangle. So same idea, right? Area of the red. Base is still 2. My height now is f of 3, though. So it's going to be 2 times f of 3. That gives us 16 exactly. For my blue, I get 2 times f of 5. And you'll notice some of these are the same values from what we had for our left Riemann sum. Here we get approximately 13.333 repeating. Then we have area of the orange. So I get 2 times f of 7. Which is 5.3 repeating. So again, what this is an estimate of is the same thing as up above. It's the estimate of the integral from 0, hope I did 1 to 7 up above. Integral 1 to 7 of f of x dx is approximately, well, if I add those all together, I get 34.667, depending on whether you round or truncate. And you should notice that this estimate was quite a bit less than the left Riemann sum, right? The left Riemann sum was in the 40s. This one's in the 30s. So the estimates do vary a bit, depending on which one you use. And we'll talk a little bit later about, which estimate may be closer to the actual value, depending on what the function looks like. And there's some characteristics of the function that, you can use to determine which estimate may be the better one. But we do have a couple more to do. We're going to move on to the midpoint Riemann sum. There's a couple more right Riemann sums that you can do. I guess this is one question to think about before we go on. Before we continue, what inference can you make about the approximations as the lengths of the rectangles decrease? So they're talking about the distance along the x-axis. So essentially, let me just draw some right Riemann sums for us. I don't think we need that question there anymore. We can remember what they were asking. Just make the graph as big as possible. There we go. So let's say I do some right Riemann sums. Let's try to draw these well. Okay, so there's there's a Riemann sum broken into intervals of 2 from 1 to 7. Now let's say I broke them into intervals of 1. I'll do those in blue. Still doing a right Riemann sum though. And we can think, do we think the blue is a better estimate, or do we think the red would be a better estimate? And we could even go further. We could break them into intervals of 1/2. One's going to be a little bit harder to draw. Getting the sense this doesn't look at, this may not be as beneficial to you guys as I thought it was when I first thought about drawing it. But essentially, as we make these rectangles smaller and smaller and smaller, and here's what I'm going to do. I'm just going to do one rectangle over one subinterval. So we're going to go from we're actually going to go from 0 to 2. I think that'll make the most sense. So let's go from 0 to 2. So if I do a right Riemann sum for one rectangle, it's going to look like that, right? So let's think. If I broke this into two rectangles and I still did a right Riemann sum, let's do it in blue. I'll try not to overlap them actually. Right, which do we think is a better estimate of the area? I'm going to sketch it in here, of the area underneath this curve. Right, do we think it's the pink rectangle or do we think it's the two blue rectangles? Well, it's going to be the two blue rectangles, right? The pink rectangle includes this extra area right here that is not part of the actual area. So the pink rectangle is going to be farther off. It's going to be a much, it's going to be a higher number than blue when the actual area is even less than what blue is. So as we continue to make the number of rectangles, as we continue to increase the number of rectangles we use, our estimate gets closer and closer and closer to the actual value of the area under the curve. So the examples that we're doing on the video are where each rectangle has a base length of 2 units. As you try some of these on your own, where you split the base length into 1 unit, then half unit, etc., the numbers that you're getting, they're going to be closer to what the actual area is, even though we don't actually know what that area is because we don't know how to find that yet. We just have focused on finding approximations. But that is a key idea. As the number of rectangles increases, the approximation gets closer and closer to the actual area. Okay. Like I said, we do have 2 more approximations to do, so we should get to those. Next one is midpoint, a midpoint Riemann sum. And again, we'll do the one on the left. Same interval, same function, just a different way of doing it. So when we're doing a midpoint Riemann sum, well, we're still going from 1 to 3 because our subinterval is 2 units. But now the height of this rectangle is going to be based off of the midpoint between 1 and 3, which is 2. So we're actually going to go up here to where 2 has its y value, and that is going to be what we base the height of our entire rectangle on. Same thing from 3 to 5. It's going to be 4 that decides how high our rectangle is. Maybe you're already thinking, this seems like a better estimate than either right or left Riemann sums, and you would be correct. This is a better estimate. Estimate's probably better than my drawing. Okay, so now we just still have 3 areas to find. For the red, it's going to be 2 times f of 2 this time. Two times f of 2 is 15.3333 if I round. For the pink, it's 2 times f of 4, which is actually going to be the same thing as f of 2. And then we have the area of the blue rectangle. So 2 times f of 6. F of 6 lands directly on 5. So we end up getting 2 times 5, which is just equal to 10. If I add all three of those together, that gives me 40. Let me do this over here. You know what? Let me just do the whole thing. So again, this is our estimate of the integral from 1 to 7 of f of x dx. And our estimate is 40.667. And you'll notice that midpoint approximation was between our left Riemann sum approximation and our right Riemann sum approximation. The midpoint is a better approximation than either the left or the right. It's going to be closer. So those are the three approximations if we're using rectangles. There is one more that we need to look at, and it is the trapezoidal approximation. This one's a little tougher just because the area formula for a trapezoid is a little more intense than the area formula for a rectangle. So let's talk about how to do this. There's only one type of trapezoidal approximation, so you don't have to worry about left, right, midpoint, etc. Same interval, 1 to 7, and same subintervals. We're using length of 2. So for my trapezoid, I have to look at the y values for both of my endpoints. And then I connect them to draw my trapezoid. So there's my first trapezoid. Here is my second. And here's my third. And now I got to find the area of each of those. So the area of my red trapezoid, again, area of a trapezoid, 1/2 times the sum of the lengths of the bases. So I'm going to have 1/2 times the quantity f of 1 plus f of 3 times the distance between my bases, which is going to be 2. I'm actually going to write all of these out here first. Area of my blue trapezoid, 1/2 times the quantity f of 3 plus f of 5 times 2. And for my pink, 1/2 times quantity f of 5 plus f of 7 times 2. Now, you'll notice one thing here, right? These 1/2s and the 2s all simplify. So you could do those, or you could just notice that they all simplify right away. So you're really just adding the two bases together. That's only because our subinterval here is 2, right? If our subinterval here was 1, then they would not simplify out because all the 2s would be 1s, etc. So let's figure out what these three areas are. For the red trapezoid, we get approximately 14.6667. For the blue, same thing. And for the pink, that one was smaller. We get 9.3333. And if I add those all together, then my estimate for this integral from 1 to 7 of f of x dx is approximately 38.667. And you've probably noticed that The trapezoid rule also seemed like a pretty good approximation, much better than the left and the right Riemann sums for rectangles. You're correct. The trapezoid and the midpoint are the better of the four approximations. There's not a clear-cut winner between trapezoid and midpoint approximations. Sometimes one is better than the other depending on what the function looks like. We have gone long enough. I think we're just over 30 minutes. So we're going to stop the video here. There's plenty of other practice for you to do. And we're also going to take a look at how can we do these approximations when we're not given the actual graph, when we're just given a table of values. Can we still pull off these approximations? So as always, enjoy the rest of your day, and we will look forward to seeing you next time.